In this video, we're going to be adding geometric vectors, and we're just going to start with an introduction of adding geometric vectors. Note that vectors can be moved around in space if you do not change their length or direction. So adding vectors. When you add two or more vectors, you are finding a single vector called the resultant that has the same effect as the original vectors applied one after the other. The sum or resultant of two or more vectors can be found in several ways. In the triangle law of vector addition, draw the vectors so that the tip of one is at the tail of the other. The resultant is the vector joining the tail of the first with the tip of the second. So as you can see here, we've got u and v added tip to tail, and then the resultant goes from the tail of the first to the tip of the second. There's also the parallelogram law of vector addition, and you can see the diagram to the right here and page 12 of the text for details. The two laws of addition are equivalent. In the triangle law, the vectors are arranged tip to tail. In the parallelogram law, the vectors are arranged tail to tail. So you can see right here, u and v are right here, they're tail to tail, and u plus v, if we form a parallelogram, forms the diagonal right here. Okay, subtracting vectors. To subtract two vectors, we add the opposite of the second vector. So u minus v is just equal to u plus negative v. Vector's law state that you may add vectors in any order you like, the commutative and associative laws apply, and that you may expand in factor expressions in the usual way. So the distributive law also applies. So all of these right here are properties of vector addition, properties of scalar multiplication, and properties of the zero vector. You can review these on your own right here, but they're no different than what you would expect them to be. Okay, so if we have right here, we've got basically a 3D prism. And we have vector A running along the base here from O to A, vector B running from O to C, and vector C running from O to D. Express each of the following vectors in the rectangular prism in terms of A, B, and C. So if I want to go from B to C, well, B to C is basically the same thing, and I'll show you right here. B to C is the same thing as C to B, right? Which is the same thing as A. But B to C is the same in magnitude as C to B. However, it's in the opposite direction. So as you can see, B to C is the same magnitude as A, but in the opposite direction. So we just say negative A. G to F is the same as, if we look up here, okay, I'm just going to flip this vector right here. Let's go back to where it was. Okay, so G to F goes along this portion of the prism. G to F is the same in magnitude and direction as A, so that's just equal to A. So we'll write it over here. This is equal to A. Now, O to B is a little bit interesting because O to B actually forms a diagonal, right? And you can see that we can get from O to B by going from O to A and then A to B. So that means we can take the A vector and we can add it with the B vector if we took this B vector and we moved it right here. Remember, you can move a vector in space so long as you preserve the direction and the magnitude. So OB, this diagonal right here, is just the same as A plus B. AC, we can see right here. I'll delete this one. And I'll insert the AC vector. Okay. AC would be the opposite of A plus B. So the opposite of A is negative A plus B, which we can then simply write as B minus A. And B to G would be as follows. So we have B to G right here. So that is going to be, effectively, we're going to have to go the negative of A and then the positive of C. So that's the negative of A direction plus the C direction. So then we just go C minus A. O to F, that goes from here, this corner right here, all the way to F. Okay. And so then we get A plus B plus C, like that. Okay, good. All right, what single vector is equivalent to Mn negative Pn plus Rq and Pr? Remember that vectors are added from tip to tail. So we have to add from tip to tail, and we have to kind of remember that, like, if I do vector Mn, this right there is my tail, and this right here is the tip, okay? So if I want to add these, the tail of one must line up with the tip of another. So I can't add these as they are currently because n, the tip of this one, does not line up with the tail of this one. But we can remember that negative Pn is just equal to the opposite of, or it's just equal to Np, right? So Pn is the opposite of Np, and if we put a negative right there, we just get Np. So what I'll do right here is instead of minus Pn, I'm just going to say plus Np. So Mn, and again, instead of negative Pn, well, negative Pn is just positive Np, plus Rq. Well, I can't do that because the tip of this one does not match the tail of this one, so let's delete that. But I can rearrange and put my PR right here, and then RQ, and I'll get MQ as a result. Okay, finally, given that vector m is equal to 2a plus 3b and vector n is equal to a minus 4b, simplify 2m minus n. Okay, so m is 2a plus 3b, so I go 2a plus 3b. However, I have to put a coefficient of 2 in front of that, and then minus, and then over here I'll have a minus 4b. Okay, so this 2 distributes in, I get 4a, then I get plus 6b, then I'll get minus a, and then plus 4b. So that's 3a plus 10b. Okay, so that's like the elements, or like the essential elements of vector addition, okay? And that's just an introduction. There's some homework here listed, okay? And you can give these questions a shot.